Welcome. I want to say something about Euler characteristic for quivers. So for graphs, finite simple graphs, there's a very nice notion of Euler characteristic. You take the Euler characteristic of the finite abstract simplicial complex defined by the graph. So you look at all the complete subgraphs. This defines you a finite abstract simplicial complex. It defines you a exterior derivative. It defines you cohomology, and so you can compute the Euler characteristic in different ways, and you have nice theorems. So theorems are nice if they are equating two numbers and it's not obvious that these two numbers are the same. For example, Gauss-Bonnet theorem, you add up the curvatures at every point, and in full generality, any dimension, you have this theorem in the continuum limit. You get the Gauss-Bonnet chain theorem for manifolds, for even dimensional manifolds. But this is general graphs. You don't have to have any manifold structure at all. So this is very, very general. Also, Euler, the Poincare-Hopf theorem is very, very general for any injective function, any coloring function which is different on different nodes. You have a notion of index. It's actually a divisor, and then you add them up and you get the Euler characteristic also. And if you average over all functions, you get the usual curvature. So this is also true in the continuum. Everything is parallel. Euler-Poincare, I will say something a little bit about that. So there are two different ways how you can look at Euler characteristic. One is a homological definition using Betti numbers, and one is a combinatorial definition where you count stuff. And there is a nice kind of generalization of Euler characteristic in a dynamic way. If you have a automorphism, so for T, the identity, this is the usual Euler characteristic. For a general map on the geometric space, you have a Lefschetz number, which is the supertrace on the cohomology, which is then also equal to the sum of the indices. This can be used to prove that there are fixed points. Like, for example, if the cohomology is trivial, if you have a contractible space, then you have automatically a fixed point. And then McKean Singer, one of my favorite theorems, which tells us the Euler characteristic is the supertrace of the heat kernel. And that's actually very, very, I mean, maybe I will say something, this gives you lots of things. For example, this Brouwer-Lefschetz or Euler-Poincare can be proven directly from the heat flow. There is a nice theorem of Riemann-Hurwitz. If you have an action on a graph, here one has to assume it's not very, I mean, most general, you need to have a barycentric refinement, otherwise the things are too degenerate. If you take you get something like an orbifold, you don't want that. You want to have a manifold or kind of a graph again in this case. And then Riemann-Roch, it's one of the reasons I'm looking at things a little bit differently now. Since 10 years I tried to kind of get a grip a little bit on Riemann-Roch to see this as an Euler-Poincare formula, which is an open problem of Baker-Noreen. This is a Baker-Noreen theory for graphs, which however look at graphs as one-dimensional objects. So we don't look at graphs as one-dimensional objects at all. So this graph here has two triangles. This is a two-dimensional object. So it has no, so there's a zero-dimensional part, a one-dimensional part, and a two-dimensional part. In general, you have geometric realizations of these graphs are objects, higher dimensional objects. In special cases are manifolds. So this is not just one-dimensional like many graph theorists look at graphs, but this is very, very general. So what do we want to have? There are some properties which we want to have for Euler characteristic which hold for graphs. It should be invariant on the homotopies. That's something nice. It should have the rule of sums. It should satisfy that if you this inclusion-exclusion property, if you take the Euler characteristic of one object, the Euler characteristic of another object, they add if they are disjoint. But if they are not disjoint, it should just satisfy the obvious things, that the union is the sum minus the intersection. So that's also called evaluation. There are many valuations on graphs, and that's a linear space of valuations, and every valuation has also corresponding theorems like Euler like Gauss-Bonnet or so. But there is only one of these valuations, which is barycentric invariant. That's the Euler characteristic. You also want to have the normalization that the one-point graph or contractible graph in general then has Euler characteristic 1. And very important, that's the litmus test. If an Euler characteristic does not satisfy the rule of product, the product is the property that if you take the product, Cartesian product, here the Shannon product, of course for graphs we talked about this a lot, the Shannon product is the right product for graphs, and you want to have that the Euler characteristic multiplies. So it's even more true here for graphs that even curvatures multiply. So the curvatures tensors nicely, and of course you also want for spheres that it satisfies the Euler characteristic 1 plus minus 1 to the n, which is called Euler's gem formula, which is quite interesting historically. And you have something here a little bit historically. Francesco Mauro-Lico, even 100 years before Descartes, there's this famous story of Descartes who kind of discovered this Euler formula, number of vertices minus number of edges plus number of faces is equal to 2. That's actually for 2 spheres. That's a very special case for 2-dimensional spheres, polyhedral formula. So he found that, but only looked at the regular Platonic solids, and so he just saw this rule, and René Descartes even was so excited he was writing it in an encrypted form in his diary, and that got lost, and Leibniz translated it. It's a famous story, which is Descartes' secret notebook, a book where you find that. By the way, Mauro-Lico, story about Mauro-Lico, that's Michael Friedman's book about folding, his folding book, which is actually quite recent. I did not know about this before I saw this book, that I thought Descartes was the first who had this, saw this. But Euler was really the one who proved it first, and so there's a big difference between seeing something for special cases happening, or to have something which is a conjecture that something holds for a large class of objects, like a convex polyhedra in R3. So that can be defined nicely there, because you have a notion of face. You want to have a notion of face and a notion of edge and a notion of vertex. If you don't do that precisely, you are in big trouble, like in a 4-dimensional. This is a 4-dimensional object, actually, I mean, considered kind of a, but you have to kind of say what the faces are, so you don't want that mess. And one of the ways to get out of this mess, of which Lakatos very nicely described in his book, is to actually look at the graph, and then you define a simplicial complex from it, which is the set of complete subgraphs, or the vertex sets of complete subgraphs, which is a finite abstract simplicial complex. No geometric realizations at all. Don't look at infinity axiom. And then you have a nice notion of Euler characteristic there, which is equivalent to the cohomological, and the combinatorial definitions are the same by this Euler-Poincare formula. So that's very nice. And then, but it's really kind of these are kind of just seeing the rule, but not actually seeing the theorem. Euler saw the theorem, and then Poincare and others, it actually becomes complicated here with the history, have then seen this in higher dimensions, like Schläfli also, or Stout. And so there are many different mathematicians who have then kind of worked also on the higher dimensional case, also fleshed it out, what happens in general, you know, not only for spheres. For spheres you have this. For even dimensional spheres you have 2. For odd dimensional spheres you have 0. Like for a circle you have 0. For 3 spheres you have 0. And so on. And then so Hopf was one of these giants who has kind of then, here in Poincare-Hopf, who has really, he mentions also Emmy Noether, who kind of saw how nice it is to have the algebra. This is kind of the start really of serious algebraic topology. And then also maybe one should, in the context of multiplication, the multiplicative property, one should probably mention Eilenberg. Zilber. Eilenberg is really the person who kind of started, one of the person, Algebraic McLean, who started category theory. So this is in the 50s, and Silber is an interesting case. I like that. So he wrote a paper with Algebraic in the 50s, right, 1950, and actually in other papers which were quite important in the annals. But he made then his thesis in 1963 as a 40-year-old here with Andrew Gleason and Raoul Bott. So that's kind of an interesting case. So 13 years after even kind of this groundbreaking paper, kind of understanding what happened. How do you deal with multiplicative structure, which is quite a challenge a little bit before. How do you do that? How do you actually find a Cartesian product which has all the nice properties? The Shannon product really does the job, and so you have a nice ring structure, and you have a nice arithmetic, and everything is compatible. The Euler characteristic is nicely behaving with respect to the sum of the objects as the sum of the Euler characteristic and also the product. So that's what you want to have. Rule of product is something you know from middle school. That's what you learn. It's a very look it up rule of product. This is a generalization. You don't want to have any notion of Euler characteristic which doesn't satisfy the rule of product. Now, I was thinking about quivers more recently in the context of spectral theory, and just thought about, how can you generalize all this from graphs to quivers? It turns out to be quite interesting. So in order to do that, and I also pondered for many years now already, there's a problem here in Riemann-Roch for graphs. How do you actually interpret these notions here? These are notions. How much energy do you have to add to a divisor in order that it becomes an essential divisor? So this is kind of these are hard to compute notions, but then you have the Euler characteristic of the divisor, which is the Euler characteristic of the underlying graph plus the degree of the divisor, can be written as a difference. This is the canonical divisor here. So what one wants is to see this also as an Euler-Poincare formula, to see this as a sum of petty numbers. This is a sum of petty, so positive petty numbers and negative petty numbers. So that's kind of something which I hope to get into here with the concept of quivers, because there's something nice here. So first of all, if you look at the quiver, so you have these additional loops, but there is a change of point of view which you can do. You can, especially in the context of Riemann-Roch, you don't look at them as edges anymore. You look at them as vertex excitement. So this is more excited. So it's like a quantum mechanical oscillator which you can attach to every vertex. That's what one calls a divisor, just an integer value at everything. You take this as vertices, and then you have the edges. They can also have multiple edges, and I can see this is a data structure which you can very well introduce in a computer. I did that actually this week. I kind of all this is implemented in a computer algebra, so you can compute things. So what you have is kind of a seed for and now you have to introduce a delta set. You have a delta set instead of a simplicial complex which is associated to a graph. You have then a delta set, which is just a set of sets with some boundary maps. So it's not as complicated as a simplicial set, which come here kind of more in the fancy world. So it is considered a pre-sheaf over the simplex category. So that's kind of something which where you scratch your head. And but also this is a pre-sheaf on the simplex category with a strict so the morphisms are just a little bit restricted. So that's important to see that this is more general than that, because you have here more structure. You have also degeneracy maps, and while here you have only the boundary maps, the DI, and here you have the DI and the SI. So you know about the simplicial sets. So this is actually more general. And it's also easier to work with, especially with a computer. So what you do is when you build that with a computer, and so first of all, This can be done in a few lines of code. So you take from this seed, you produce then a simplicial set, which is a kind of a delta set, which is actually just a sequence of sets with boundary maps. So you have also to specify the boundary map. 5 minus 6 plus 3, that's 2. So the Euler characteristic is 3. So it's the alternating sum. It's like what you have here when you define the simplex generating function here. It's 1 minus f of minus 1, which is the alternating sum, the number of zero-dimensional parts plus the number of minus the number of one-dimensional part plus the number of two-dimensional part minus the number of three-dimensional parts, etc., etc., etc. You do that and you get a notion of Euler characteristic. But this can also be expressed using cohomology, and that's actually very, it's kind of more, still quite a traditional thing. You need a little bit of linear algebra. You have to define these exterior derivatives. So what you have is you have the gradient here. So that's the gradient here. This is the gradient, and then you have the, so this is the divergence here. And then you have also the curl. This is the curl. And that's the dual of the curl. So what you have is this defines your calculus. Right? You have the calculus. In this case, you have two-dimensional calculus because it's a two-dimensional space. So you have all the theorems, of course, Green, fundamental theorem of line integral, not yet Stokes divergence theorem because we are not yet in 3 dimensions, but this is all working very well. You have the Hodge Laplacian, and then you look at this decays into blocks. These are these Hodge blocks, and the kernel of L0, that's the zeros cohomology group. The kernel of N1 is the first is the harmonic 1 forms, harmonic 2 forms, harmonic 0 forms. Their dimensions are the Betti numbers, and then you can compute the Euler characteristic as B0 minus B1 plus B2. So this is usually called also the genus, and so it's 2 minus 1 plus 1, which is also 2. Now, why are they the same? This is actually kind of something I learned from Benno Ekman. He was also kind of a great expositor, speaker. So there was a seminar once at that was at the University of Zurich, where he gave a talk about Euler characteristic. And so it's very, very simple. It's actually something you can do with in a linear algebra course. So what you have is, first of all, you have the space. So the space is kind of the space of k-forms, which is in this case a 5-dimensional space, 6-dimensional space, and then a 3-dimensional space. These dimensions are the Fn. These are the F vector. This defines with the F vector here, which become 5, 6, 3. And then you look at the kernel of Lm, and you look at the rank. Then the rank and rank-nullity theorem that tells you that the sum of them is equal to the number of columns, which is in this case just Fm. So that's one of the equations you get. But then you have also the cohomology groups, which satisfy, the dimension is Zm minus Rm minus 1, because the image of Rm minus 1, the range, the image of the Dm minus 1 is, that's the rank. The image of the Bm minus 1 is contained in the kernel of Dm. That's kind of one of the properties which kind of you have for this exterior derivative, basic property which you want to have a chain complex. And then you have this and you have this relation from that. So from that, if you add them up, you get this, and then you sum it up. Then what happens if you have to take the alternating sum? The super sum will produce these cancellations, and then this is super sums to 0. And so that's why the super sum of Fm is the same as the super sum of Bm. That's the Euler-Poincare formula. So that's something which is here very elementary, and I think one has to attribute to Ekman that he saw this. That is also this Hodge theory, something which is working very, very well. And that Dirac and Hodge, that's like oxygen and hydrogen together, reproduces all this kind of nice mathematics. So this is very nice. And yes, so one has this also here for in this more general setup. One has still this equivalence of Euler characteristic. Now you go and you look at all these theorems, whether they hold. So Gauss-Bonnet is no problem. You take the thing, you take the objects which you have, and then each of the objects, each of these objects has weight -1. Each of these objects has weight 1, and you put them onto the vertices. And if you put them onto the vertices, then you have a curvature on the vertices. That's what this Gauss-Bonnet about. You do the same thing with Poincare-Hopf, depending on just what the function tells you where to put things. And that gives you then integer values, because all these integers remain integers when you move them. These we have just seen. Brouwer-Lefschetz is actually seen best using the heat deformation. Also this, by the way, can be seen by heat deformation. If you take e to the minus tl, what happens is, because all the eigenvalues are positive or 0, what happens when you take e to the minus tl, all the stuff which is related to positive eigenvalues goes away, and only the kernel remains. That's why you have when you take the supertrace of 1, you get the Euler characteristic by definition. If you take t equal to 0, then you get the when you take t equal to 0, you get the Euler characteristic by definition. If you take t equal to infinity, you get the cohomological Euler characteristic, because it's the alternating sum of the super sum. Then is the alternating sum of the kernel dimensions, and that's what is also this Brouwer-Lefschetz can be done just in the same way by heat deformation. You can get that for t equal to 0. When you take the t equal to 0, you get the sum of the indices of the fixed points, and then when t goes to infinity, you get this alternating sum of the heat of the induced map on cohomology, which is then defined as to be the Lefschetz number. Holds in very general terms also here, no problem. And Riemann-Hurwitz is kind of a nice thing. I should actually talk a little bit more once about this. This is kind of when you have an action of an abelian group on the geometry. Then so what you have is actually branch covers. So this is kind of the part of the branching where they have identifications. So you can see many spaces as branch covers of simple spaces. Riemann-Roch, here I have still to work more on that. That's actually very interesting. The question is, can you actually express this L of D? So this is a very, very interesting thing. So this is also, and one of the reasons why I like to move these loops onto the vertices, so to see them as divisors. So you can actually work with objects which appear in Riemann-Roch, and also you can look at negative divisors, and so you have then hopefully kind of a similar framework. But hopefully this is just the sum of the Betti numbers of the positive part of the Euler characteristic, and then there is also a negative part of the Euler characteristic, because the objects can become negative. So this is kind of an interesting thing I have still to look at. Also this, I don't yet know what is kind of the good notion of homotopy here, so you have to kind of to look at that, and in this case it should also be that this linear equivalence you have here is actually part of a homotopy. So you should see this as homotopy. This should be something which is homotopy invariant. And then this, also the rule of the product, that's actually one of the main reasons why I moved the loops from edges to the vertices. If you take the edges and you take the definition, the Shannon product definition, there it produces a mess, and probably also here. It's just you don't have so nice things to work with, because you have kind of identifications like objects like 1, 1, 3, and then you have to decide what you actually want to do. How do you actually? But still, it should work also. I don't see any reasons why it should not work, because once you have a something like this general as a delta set, then you have also a cohomology, and you have also an Euler characteristic. But still, then the question is, no, also that should be simple enough to continue. But one of the reasons why two reasons why I really want to move the vertices to the loops to the vertex thing is here, and another reason is the product. I want this Euler characteristic to be compatible with the Shannon product, and so this is hopefully also curvature. I don't yet know. Also, hopefully curvature should be compatible. I don't yet know about Euler's gem. So one has to know different. Once you have a notion of homotopy, you have a notion of sphere. So notion of sphere needs the notion of homotopy and needs the notion of notion of contractible. Then you can define sphere. Sphere is a manifold, which is when you take a vertex away, becomes contractible, and every unit sphere is a smaller dimensional sphere. We talked a lot about this. But then once you have that, it's clear that so this Euler gem formula holds always for that by induction for this structure. So yeah, maybe this is something more to work about, and I stop here.